Okay, guys, happy Wednesday. It's me, it's your math teacher. I'm obviously not here today. I wish I was, but I kind of am, but I'm actually not. But we're gonna still run class kind of the same setup. So, with that said, this is your warm up for today. I'll give you guys about 3 to 4 minutes to work on this. It's all exponent properties, same thing we've been doing the past 2 days. So write these down, put in your notebook, give it a shot. I'll give you, again, about 3 to 4 minutes to work on it. Also, be nice to the sub, whomever it is. Unless it's Mr. Patterson. You can be mean to him. So again, just a reminder, for the exponent properties, there's no real order to go in, but just go base by base. And normally I recommend dealing with all the negatives last. The fourth one on here is kind of a special one. It's gonna come into play today. So if you get it, great. If you can't figure it out, just wait until I explain it in a couple minutes. Give you guys one more minute. Okay, let's go over these. I don't know if that was enough time. Hard to judge without actually seeing you guys. Anyways, we'll go over. If you didn't finish, that's fine. We'll just go over them anyways. The first one's one of the ones where, again, it's one of those things in math where, there's multiple ways to get to the right answer. And that comes with the definition of exponents. Exponents is just a repeated multiplication. We know from the number properties that multiplication has the commutative property. With that means that the multiplications can go in any order. And it's kind of the same with the properties. The properties are all just kind of reworkings of the same thing. So it's all this reworkings of multiplications. And since multiplying works in any order, the properties also can be worked in any order. So something like this first one, there's kind of two trains of thought on this. You can, one, use what we call the power property, or the power of a power property. And that's when it happens when you have an exponent raised to another exponent. When you have an exponent that's raised to another exponent, like in this problem, where we have 3 squared raised again to the third power, or to the cubed power, we know that if you have a power raised to a power, you multiply those powers together. So your one way of doing this is to figure out that, we'll keep the base the same with 3, and then we'll multiply the exponents together to give us 3 to the 6th power. The other train of thought for this one is, well, you could simplify the base right away. 3 squared, and again, a lot of our bases are variable bases, but in this case it's not, it's a number base. It's 3 to the 2nd power, 3 squared, or 3 times 3. So your second train of thought for a problem like this would be, let's simplify the base and then raise it to the power. If we simplify the base itself, which is 3 squared means 3 times 3, which is 9, then really we have 9 to the 3rd power. Now, if you use a calculator, or if you use your, you do it in your head, again, it's just repeated multiplications. 3 to the 6th power means 3 times 3 times 3 times 3 times 3 times 3, whereas 9 to the 3rd power means 9 times 9 times 9. Whichever method you choose, you're going to get the same answer. 3 to the 6th power is 729. And 9 to the 3rd power is also 729. So again, this is one of my favorite parts of math, where there's always multiple ways to get to the same spot. Okay. Obviously, both answers are the same. Either way you get there, it doesn't matter. I don't have any preference for that. As long as you get 729 in the end, that's good. And realistically, you could also just kind of type that into the calculator all at once. Second problem. I'm going to go through these a little faster just so I don't make this video 40 minutes long. Another power property. If you have, a bunch of stuff, whether it's multiplications, divisions, if you have a bunch of things in parentheses, a bunch of bases in the parentheses, but you have an exponent on the outside, my recommendation for this is that you distribute. And again, when I mean distribute, I don't mean the distributive property. I mean you give each base that 3rd power. So this one has a lot of bases in it. We're going to have to give the 2 to the 3rd power. Now again, this is where people get confused. They think, all right, we're going to multiply 2 times 3. We're not. We're going to do 2 to the 3rd power, which is very different than doing 2 times 3. And then we're going to take our x to the 3rd, and we're going to have to raise that to the 3rd power. We're going to take our y to the 0, and we're going to have to raise that to the 3rd power. You also have to worry about the denominator. We're going to take the 3 and raise that to the 3rd power, and then we're going to take the z and also raise that to the 3rd power. Okay. So we have 5 different bases all being raised to the 3rd power here. We know that when we have a power raised to a power, we multiply it. The 2 doesn't have a power on it, so it's going to be 2 to the 3rd. The x does have a power on it, so we're going to have to multiply that power by the outside power, 3 times 3, which gives us x to the 9th. Same thing with y. Y is raised to the 0 power. Again, you can use the 0 power property here and say that, that's just a 1. But for the sake of this, I'm just going to leave it as y to the 0. 0 times 3 is 0. Again, multiple ways to do this. 3 to the 3rd, z to the 3rd. And that's pretty much it. As far as simplifying goes, well, we know that y to the 0 power is just 1. We kind of already mentioned that already before. And then since we have these numbers and they're small enough, 2 to the third power means 2 times 2 times 2, which is 8. Stub x to the 9th on top. My cat is going through the trash right now. I'm going to have to stop that in a second. 3 to the third power is 27. 3 times 3 times 3. Yeah, so they're right. And z to the third power, which is z to the third. Okay, just going to pause real quick and get my cat out of the trash. Alright, we're back. Cat out of the trash. I forgot how fun it was to make these videos. I haven't done it in a while. Third warm up. Again, go base by base. This warm up, we have the number bases, we have the x bases, and we have the y bases. Go step by step. I prefer dealing with all the negatives last. So I just go piece by piece. If you have numbers, treat them like numbers. That's what they are. This number is being divided by another number. The number base is just 8 divided by 2. Okay. For the x bases, you have same base being divided. And if you have same base being divided, we subtract our exponents. So our x base is going to have the top exponent minus the bottom exponent. And last one, our y base, same thing. We're going to have the y exponent on top divided or minus the y exponent on the bottom. And we simplify from here and see what happens. 8 divided by 2 is just division. That's 4. Subtract the x exponents, gives you x to the 5th. Subtract the y exponents, gives you y to the negative 2nd. Remember, one of our rules is that you're not allowed to have negative exponents in the final answer. So we have to change that to a positive exponent. To do that, we're going to have to make a fraction. Anything that's positive is going to stay on top. Anything that's negative is going to move to the bottom and become positive. So 4 doesn't have an exponent, but it is being raised to the first power. So it's just 4 is going to stay on top. X to the 5th power is already positive. That stays on top. Y is negative, so we're going to move that one to the bottom. All right, and the very last one. This one's a little tricky. It's a little different. These are going to come up today in today's lesson. We have a base of 3, a power of x plus 1. Okay, so this is the first time we've seen an expression as a power. That can happen. And then that whole thing is being raised to the 5th power. Okay. Same thing is going to happen here. We have a power raised to a power. Now our power in the parentheses is an expression. The exponent, and we talked about this at the very beginning of the year when we talked about order of operations. The exponent part of the exponent part piece is considered a grouping symbol. Just like the top of a fraction is considered a grouping symbol, or the bottom of a fraction is considered a grouping symbol. This x plus 1 is grouped together. It's not 3 to the x and then 3 to the first. It's 3 to the entire quantity x plus 1. Okay. With that said, we know that a power raised to a power is a multiplication. So we know that we're going to have to multiply these two exponents together. Okay. Now it's very important that you do group these x plus 1s together. Okay. So if we do a quick rewrite of this, what we're really finding is we're finding 3 to the x plus 1 power times 5. Power raised to a power, we multiply. Okay. So even though we're used to the distributive property going forwards, you could also use the distributive property going backwards. Again, it all ties into this idea that multiplication is commutative. The order in which you do it doesn't matter. So you can use the distributive property backwards, and we've done that before. So that's what we're going to do here. We're just going to distribute that 5 throughout that exponent. Which gives us, using distributive property, 3 is the base, stays the same. That has nothing to do with the exponent part of it. The base is always going to stay the same. And we got 5 times x, which is 5x. And then 5 times 1, which is 5. 5x plus 5. And this is what we're going to consider simplified. Okay. And that concept is what we're going to be using in the lesson, which I'm going to start right about now. Okay, so what are we going to talk about today? We're going to talk about solving exponential equations. We have these exponent properties, which are, again, all just reworkings of the definition of what an exponent means. But we have these properties, and how can we use them? Well, one way we could use them is to solve exponential equations, which is, again, solving equations, one of the core ideas of Algebra 1. Okay. What makes it an equation, an exponential equation? An exponential equation is any equation that has a variable and an exponent. So the equations we've solved so far have been all linear equations. Linear equations are all in line. They all have just a degree of 1. We haven't dealt with any variables ever in the exponent. To solve these types of equations, these exponential equations, we need one property. Okay, it's a property of exponents. It's a property of math. It's called the power property of equality. Power property of equality. Again, you don't need to know the name of it. You just really have to know how it works. Just like a lot of the stuff, all the exponent properties. Don't care if you know the name. Just know how they work. All right, the power property of equality, I'm going to give the mathy definition. We'll write down the mathy definition. And then I'll explain it kind of in a little easier terms. Power property of equality states that if these variables are going to come up in a second. If b is greater than 0, b referring to your base, and b doesn't equal 1, okay. These are all just, both of those are just qualifiers of what makes something exponential. Okay, negative exponents with negative bases act differently, and if your base is 1, then it's 1 to any power is always going to be 1. That doesn't act like a exponent. So these are just qualifiers that make sure that something's an exponent, or make sure that something's an exponential equation. Okay. So if your base is greater than 1 or greater than 0 and your base doesn't equal 1, then in a lot of math properties and theorem things, it's always an if-then statement. So if this happens, then this will definitely happen. So what happens? If your base is greater than 0 and your base doesn't equal 1, then if you have a base raised to an x power, and it's set equal to the same base set to the y power, the only way those can be equal, and the way we say that in math is if and only if, the only way those two equations can be equal, the only way two equations with the same base can be equal, is if their exponents are also equal. So if and only if x equals y. So that's the power property of equality. So if you're given a statement that says these two exponents are equal to each other, and they have the same base, then their exponents also have to be equal to each other. It doesn't matter what they are. Just a side note, if and only if is a strong mathematical term. Just a little math fact. If and only if is represented a couple different ways, one of which I use a lot, which is the double arrow. If and only if means it has to work both ways. If it works forwards, it has to work backwards. In logic and some proofs in math, you'll see it written as IFF, if and only if. All those mean the same thing. It means if it works one way, it has to work the other way. All right, so what does this mean in words that we understand? It means that if the bases are the same, the exponents have to be the same. So we're going to start off with some easy examples, and then we'll get into some harder ones. All right, for example, if m is your base and you have m to the x power, and we have it set equal to m to the third power. if the bases match, that's good. We could basically stop thinking about the bases. If the bases match, we stop thinking about them. And in this case, they do match. We have m to the x and m to the third. Both have a base of m, so we can kind of stop worrying about the bases itself. Okay. I cross them out just because they already match, so we don't need them anymore. Okay, we're not crossing them out because they don't exist, but we're just crossing them out for the sake of this. All right, so if their bases match, that means their exponents have to match, okay, which means that x has to equal 3. Okay. All right, so when we're doing exponent properties, we weren't solving for x. In these problems, we are going to be solving for x, or whatever the variable is. Okay. We're trying to figure out what x value makes these equations true. In the second example, let's do 8 as a base. 8 to the 2x minus 1 power is going to be set equal to x equals, or is going to be set equal to 8 to the 11th power. Okay. First thing you have to do for these is make sure that the bases match, and they do. We have 8 and 8. Once the bases match, then you go to the exponents. Okay. These exponents have to match for this equation to be true. What that means is that 2x minus 1 has to equal 11. It has to. That's the only way this equal sign can make sense. It's the only way that this statement can be true. Okay, again, according to that property. All right, and then this just turns into a two-step equation. Two-step equations we did a ton of in the first semester. They always come back. Solve for x, add 1 to both sides, divide by 2. So for this equation to be true, x has to equal 6. Okay. All right, those are the easy versions. Those are the versions where the bases match. Like everything, it gets a little harder. Again, I always think straw house, stick house, brick house, 3 little pigs, Little Red Riding Hood. Who knows? The second scenario is, what if the bases don't match? What if the bases are not the same? The power property of equality only works if the bases are the same. And this is one of these types of problems are kind of cooked into Algebra 1. Some of these problems are unsolvable. Okay, we're not going to do any of these insolvable ones. They're not solvable within the bounds of Algebra 1. When you get to Algebra 2, there are ways to solve these problems. The ones we're going to solve are going to be all solvable. What if your bases are not the same? If they're not the same, we're going to force them to be the same. And again, as long as you don't break any mathematical rules, you're allowed to change numbers into other numbers, or you're allowed to change values into equivalent values. Okay, that's one of the core ideas of math. As long as you don't break any of the rules within math. So what we're going to do is we're going to try and make this bigger number smaller. Okay, we're going to make the bigger base become the smaller base using exponent properties. Okay. And by exponent properties, mostly we mean you should know some perfect cubes and some perfect squares. Just a side note, perfect cubes are any whole number, or not perfect cubes, perfect squares are any whole number squared. you should know, again, I generally recommend knowing perfect squares from 1 to 15. I'm not going to write all those down. But things like 1 squared is obviously 1. 2 squared is 2 times 2, 4. 3 squared is 3 times 3, 9. 4 squared is 16. 5 squared is 25. Etc., etc. Perfect cubes are whole numbers that are cubed or raised to the third power. Wrote squares again. So 1 cubed, 1 to the third power, 2 to the third power. You don't have to know as many of these, but kind of the main ones are that 1 to any power is always going to be 1. 2 to the third power is 2 times 2 times 2, which is 8. 3 to the third power is 3 times 3 times 3, which is 27. 4 to the third power is 4 times 4 times 4, which is 64. And it goes on from there. So it's going to be good to know the perfect squares and perfect cubes, because that's what's going to come up in these problems. Okay. All right, so let's look at an example where we have to force a base to become a different base. So if I have an equation like 5 to the x minus 8 power equals 25. 25 doesn't have an exponent. Technically, the exponent would be 1. It's 25 to the first power. However, the power property of equality doesn't work. It only works if the bases are the same, and our bases aren't the same. I have one base of 5, and I have one base of 25. Okay. So I need to try and make these bases become the same. It is possible to make the smaller base become bigger. Okay, we can make 5 become 25 if we square it. But generally, it's easier to make the bigger one become smaller. Okay. So I'm going to leave 5 the same. 5 to the x minus 8. And then how can we make 25 become a base of 5? And again, this is where it comes, knowing perfect cubes and perfect squares comes into play. 5 times 5, or 5 to the second power, is 25. So I could rewrite 25 as 5 to the second power. And now this is an equation, the second step equation, this bottom second line equation, is something that we could solve using the power property of equality. The bases now match. We have base 5 and we have base 5, so the bases no longer matter. The only thing that matters is the exponents. For these to be equal, those exponents have to be equal. So we need to figure out which x value is going to make those exponents equal. So we got x minus 8 in the first exponent. We're going to set it equal to the second exponent of 2. One step equation. Add 8 on both sides. You get x equals 10. So the solution to that equation is x equals 10. Okay, I'm going to give you a minute to think about this problem. 27 to the x power equals 3 to the 4x minus 7th power. Goal is to solve for x, but the bases don't match, so we can't go straight into it. So you have to convert that 27 into a base of 3. And that's going to come into play with the perfect cubes. I'll give you, 30, 45 seconds to try and figure this one out. And we'll go through it. All right. So obviously we don't have the same base. So again, we can't use that property unless we have the same base. So we have to change the base. And again, we want to make the bigger base become smaller. The bigger base than this one is 27. So how can we make 27 match 3? Okay. Well, again, knowing the perfect squares and the perfect cubes is going to help a lot in this case. Think about 3 times 3 to what power is going to give us 27? 3 times 3 times 3 is going to give us 27. So we're going to rewrite 27. Instead of writing 27, we're going to write it as 3 to the third power. Okay. And that third power is still being raised to the original power, which is x. And it's going to be set equal to, we don't have to do anything to the right side. We don't change anything. All right, so now we need exponent properties. We have a power that's being raised to another power. We have 3 being raised to the x power. We know that if we have a power raised to power, we have to multiply them, and 3 times 3, or 3 times x is going to be 3x. And it's going to be set equal to what we have on the right side, which hasn't changed. Okay. At this point, this is the point we need to be at. This is the point where the bases match, and we have one exponent versus one exponent. So we're going to set these exponents equal to each other, and we're just going to ignore the bases. The bases already match, so they're good. So what we have is we have 3x. We have the equation 3x equals 4x minus 7. And we have to solve for x. Two-step equation. I'm going to go through it kind of fast just to save time. Subtract 4x from the right to the left. Whoops. Crosses out on the right side. On the left side, it leaves us with negative 1x equals negative 7 on the right. Negative 1x or negative x equals negative 7. Divide by negative 1 on both sides. So x equals 7. But it all comes back to that property, which states that if the bases are the same, and again, sometimes you have to make the bases the same. If the bases are the same and they're set equal to each other, then their exponents have to be equal to each other. So we just set them equal to each other and solve for the variable. Whoever your sub is going to give you the homework, the worksheet. Let's do evens. Yeah, we'll do evens only. All right, I'll be back tomorrow. Can't wait.